Hello everyone. Welcome to our YouTube channel. My channel, in association of Teaching Point. Like, subscribe, comment. Visit our website www.teachingpoint.org.in.
Class 11th Chemistry. Today's topic is black body radiation and photoelectric effect. First we proceed to our topic black body radiation. The theory of the energy distribution of black body radiation was developed by Planck. First appeared in 1901. According to Planck, a black body is a surface that completely absorbs all incident radiation and emit radiation at the maximum possible monochromatic intensity in all direction and at all wavelength. Here we take an object. This object is act as a black body. This object is act as a black body because it absorbs all incident radiation and emit all possible radiation. So we can simply say that a body is said to be a black body if it is a perfect emitter and absorber of all kind of wavelength and frequency. A black body is an ideal object that emits all frequency of radiation that depends only on the temperature, not on its composition. Here we take an example. We heat a black body at a temperature up to 6000 Kelvin or at 6000 Kelvin. We observe it radiate to a larger extent. When this similar object is heated at 278 Kelvin, it radiate to a very small extent. So by this comparison, we simply observe that or concluded that it is temperature dependent. Now we will move to the next topic, that is photoelectric effect. According to the statement, the phenomena of emission of electrons from mainly metal surface exposed to light energy of suitable frequency is known as photoelectric effect. The electron emitted by this effect are called photoelectrons. The current constituted by photoelectron is known as photoelectric current. We understand this effect by a simple image here, UV, which provide an incident light. When this incident light fall on the metal surface, this electron is get ejected. These are known as photoelectrons. We can understand this topic by a simple animation. Here, this is the metal plate which is act as a metal surface. This is another metal plate which is act as a detector which can absorb the photoelectron ejected or emitted by the metal surface. This is the conducting wire. Through this conducting wire, we connect an electric bulb, and this is a device which can measure the electric current. So when a light is fall on the metal surface, then photoelectron are ejected from the metal surface and reaches to the another metal rod. This metal rod absorbs the electrons, and these electrons start flowing through this conducting wire. Because of the flow of this electron, photoelectric current is developed. This photoelectric current is responsible to glow this bulb. This bulb will glow due to the photoelectric current, and we can simply show deflection in this device here. So this is photoelectric effect. Now we will proceed to the next topic, that is threshold frequency. This is very important. Threshold frequency is the minimum value of frequency below which photoelectric emission is not possible, however high the intensity of incident light may be. So we can simply say that the threshold frequency is the minimum amount of frequency that is required to eject an electron from the metal surface. Here, it depends on the nature of the metal. What does that mean? It means for different metal, the threshold frequency is different. Let's take an example of cesium and iron. The threshold frequency in case of cesium is very low as compared to the iron. That is why cesium is used in photovoltaic cell. Now, we will proceed to the next part, that is law of photoelectric emission. First point is, for a given substance, there is a minimum value of frequency of incident light called threshold frequency, below which no photoelectric emission is possible. Or we can simply say threshold frequency is the minimum amount of frequency that must be present in incident light so that electron can eject. Second point is, the number of photoelectron emitted per second is directly proportional to the intensity of incident light, provided the frequency is above the threshold frequency. Third point, the maximum kinetic energy of photoelectron is directly proportional to the frequency provided. That frequency should be above the threshold frequency. What does that mean? It means the frequency provided should be above the threshold frequency. Otherwise, photoelectron do not get kinetic energy. Okay. Fourth point, the maximum kinetic energy of photoelectrons is independent of the intensity of incident light. Fifth point, the process of photoelectric emission is instantaneous. As soon as the photon of suitable frequency fall on the substance, it emits photoelectron. Sixth point, the photoelectric emission is 1 to 1. What does that mean? For every photon of suitable frequency, one electron is emitted. Let's take one example. If one photon is fall on the metal surface, only one electron is ejected. If 10 photon is fall on the metal surface, it means 10 electron will ejected. If 100 photon is fall on the metal surface, it means 100 electron is ejected. It means the photoelectric emission is 1 to 1. Now, Einstein photoelectric equation. When a photon of energy h nu falls on a metal surface, the energy of photon is absorbed by the electron and it is used in two ways. First part is, a part of energy is used to overcome the surface barrier and comes out of the metal surface. This part of energy is called work function. So this is the photon. When fall on the metal surface, the one part of this photon is consumed as a work function. This work function is responsible for the ejection of electron. The remaining part of the energy is used in giving the velocity v to the emitted photoelectron. This equal to the maximum kinetic energy of the photoelectron, where m is the mass of photoelectron. So remaining part is consumed to convert that energy into a kinetic energy. So according to the law of conservation of energy, h nu is equal to h nu naught plus half of mv square. Here h nu is energy of incident photon, h nu naught is work function. What is work function? Minimum energy required to eject an electron from the metal surface. and half of mv square is the kinetic energy of photoelectron. When we solve this equation, the value comes to be half of mv square h nu minus nu naught. Here, half of mv square is kinetic energy of photoelectron, nu is frequency of incident photon, nu naught is threshold frequency, and h is Planck's constant. So, thus we concluded that nu naught is the threshold frequency. Nu is frequency of incident photon. Thus, if nu is less than that of the nu naught, then photoelectron will not eject. If nu is equal to the nu naught, then photoelectron will eject but not get kinetic energy. If nu is greater than that of the nu naught, then photoelectron will eject and gain kinetic energy. So for photoelectric effect, we require this third point always. It means the incident frequency must be more than that of the threshold frequency. Only then the electron will eject and gain the kinetic energy. I hope you like this video. Thank you. Hello everyone. Class 11th Chemistry. Our topic is spectroscopy and hydrogen spectrum. In today's video, we will discuss the topic spectroscopy and hydrogen spectrum. First, we will discuss atomic spectra. The spectrum of frequencies of electromagnetic radiation emitted or absorbed during transition of electron between energy level within an atom is known as atomic spectra. As you know, electron transit from ground state to excited state. When they come back from the excited state, they release energy in the form of radiation. That radiation is electromagnetic radiation. Here we take an example. N1 is the ground state of an electron and N2 is the excited state of an electron. When an electron obtains energy from any external source, the electron jump from its ground state to excited state, and after some time it come back to its ground state and releases energy in the form of radiation. That radiation is known as electromagnetic radiation. Okay, so this electromagnetic radiation may be emitted or absorbed during transition of electron between the energy level. Then we obtain a spectrum. Spectrum means color band or dark band. We obtain certain color band or dark band. That is known as atomic spectra. We explain all the things during the video. Okay. So first, each element has a characteristic spectrum. So the spectrum of each element is different. That is why it can be recognized. Okay. The atomic spectrum of each chemical element is unique. They are not similar. They are unique and is largely responsible for the color of matter. This atomic spectra also responsible for the color. Okay. Now, here are few terms that we have to understand. First, spectroscope. What is spectroscope? It is an instrument for forming or examining spectra, especially in the visible region of the electromagnetic spectrum. Here I take a picture. This picture is very old. You can easily see this candle is act as a source. Okay, here is a prism and this is a telescope. Okay, so it consists of prism. What is the role of prism? For the dispersion of radiation. And what is the role of telescope? To examine these radiation. So it is spectroscope. Second is spectrograph. It, if the telescope is replaced by the photographic film, then the instrument is known as spectrograph. The spectrograph split or disperse the light from an object into its component wavelength so that it can be recorded and then analyzed. Okay, when advancement takes place, we replace this telescope with the photographic film. Here, this is the typical picture of a spectrograph in which, in place of detector, we place this photographic film. When we expose a sample, it emits radiation. These radiations is fall on this photographic film and we obtain the spectrum. So question is arises, what is spectrum? What is spectrum? Spectrum is the pattern of emitted radiation that is recorded on the film. Here film means that is photographic film is known as spectrum. This is the continuous spectrum you can see. So you can see here are so many colors you are observing. This is the spectrum of white light. Okay. Now spectroscopy. What is spectroscopy? Spectroscopy is defined as the area of science concerned with the absorption, emission, and scattering of electromagnetic radiation by atom molecules which may be in the gas, liquid, or in solid phase. So this is whole science, whole chemistry is known as spectroscopy. Okay. Now, depending upon the nature of radiation emitted or absorbed, the spectra are broadly classified into two types. First is emission spectra and second one is absorption spectra. First, we will discuss emission spectra. Emission spectra is noticed when the radiation emitted from a source are passed through a prism and then received on the photographic plate. Okay, here I take an example. This candle is act as a source. Okay, here light is emit from this source and this light is then strike to the mirror, then grating, then again lower mirror, and then here is the photographic plate on which this radiation are fall. So here spectrum is obtained. This spectrum is emission spectrum. Why? Because this spectrum is obtained when light is emitted by the source or the sample. Okay, here we can take sample also. Okay, I take another example. Might we understand very well. This is star. Suppose this is our sun. You know our sun is a star, and you know all the sun or star are radiating the light. When this light comes from a star and this light is passed through a prism, what the prism will do? It will disperse the light. Disperse the light, and we obtain a pattern of color. This pattern is spectrum. So we call it as a emission spectrum. Why we call emission spectrum? Because light is emit. Okay, so it is emission spectrum. Okay, or emission spectra. Okay, so emission spectra are of two types. First, continuous spectra and another is line spectra. First we will discuss continuous spectra. This is continuous spectra. Why we call continuous spectra? There is no gap between the colors, or we can say there is no gap between the frequencies and wavelength. That is why we call it as a continuous spectra. Okay. So what is continuous spectra? A spectrum having no apparent break or gap throughout its wavelength range. So you can see there is no gap is present between these wavelength or frequency. That is why we call it continuous spectra. And one more thing we are able to observe, that each color is merged to each other. Okay. Now, second is line spectrum. Here you can see there are certain lines. There is a color bed and there is a dark background. In this, the background is colored and there are certain dark bands are appear. So there are some gap. Okay. A spectrum that consists of narrow, brightly colored parallel lines on a dark background is known as line spectra. Okay. So this is line spectra and this one is continuous spectra. Are you able to understand? Now we will move to the next type of spectra, that is known as absorption spectra. A spectrum of electromagnetic radiation transmitted through a substance showing dark line or bands due to the absorption at specific wavelengths. Here we can see this is source, which is act as a source, that is it may be sun, or you can take any object which can provide electricity. So this is white light. Okay. When this white light, suppose this is a sun. Okay. White light is comes from it. We place a slit. What this slit do? This will allow only a few rays which are parallel to this slit. Okay. And these rays are polychromatic. What is the meaning of polychromatic? Poly means many and chromatic means color. So this light is of many color, or we can simply say it is a white light. Okay, when this white light is passed through this prism, what prism will do? It will disperse the light. You can see there are various color. Again, this white light, this dispersed light is passed through this slit. And when this is passed through this slit, we place a sample that we want to analyze. Okay. Now, what this sample will do? This sample will absorb a certain wavelength of light and allow all the light to pass through it. And then we can able to see the spectrum on this monitor. What we will observe, this is emission spectrum and this is absorption spectrum. Okay, so this dark area will tell us these wavelengths are absorbed by the sample. By analyzing this dark band, we are able to understand what this sample contains. Because I already told you the spectrum of each element is specific. Okay, it is unique. I told you earlier. Okay, now we'll move forward. That is how our understanding till now. What is our understanding till now? So what we observe till now, that is this is a source which provide light of all color. When this light of all color is strike to the atom of the element, this atom will reflect a light of particular wavelength and allow all the light to pass through it. Okay, so the all the light which pass through this atom and analyzed, there are some color is missing. So it is act as an absorption spectra. Why we call it absorption spectra? Because light is absorbed. Okay, the light which is absorbed or reflected by this atom is again analyzed, and the spectra obtained is emission spectra, is known as emission spectra. So I think this is very good animation for you to understand how the multicolor light when passed through this atom, and this atom is absorbed. Look at this, it absorbs only orange light. This orange light is reflected back. It is, when analyzed, it is emission spectra. Rest, it is absorption spectra. Okay, so let's see move forward. Our next topic is hydrogen spectrum. When H2 gas is taken in the discharge tube, a series of line is obtained, and the region in which they lie are as follow. Here, there are certain series are obtained. Okay, these series are Lyman series, Balmer series, Bastian series, Bracht series, and Pfund series. Okay, these series are obtained when we place hydrogen gas in a discharge tube and we heated it, pass a electric current at a high voltage. Then it start radiating. When it start radiating, then there are certain series of color, certain series of band or series of lines are obtained. This series of line obtained are fall in different regions. So these regions are as follow. Lyman series is lie in ultraviolet region, whereas Balmer series is lie in visible region. Bastian and Bracht and Pfund are lie in infrared region. So this is the hydrogen absorption spectra. Okay, absorption means these light are absorbed. Okay, this is hydrogen emission spectra, in which these light are emitted. Okay, the question is arises, why this colored and dark band are appear on the spectrum? How? How it is possible? So I will tell you how it is possible. You know, we take it E1 as a ground state and E2 as a excited state. When electron is present at its ground state, it absorbs a photon of light which having a certain energy. Due to that energy, electron is jumped from its ground state to excited state. Due to absorption is this frequency, this dark band are appears. Okay, so this dark band are appear when energy is absorbed or frequency is absorbed. After some time, when this electron is comes from its excited state to its ground state, it releases energy in the form of radiation. Okay, which having a particular frequency. Okay, this color band is suggest the this frequency. So when light is absorbed, then dark band are appear. When light is emitted or energy is emitted, when electron is jump from excited state to ground state. Okay, this energy, okay, or this radiation is electromagnetic radiation having a particular frequency. So dark band is appear when wavelength or frequency is absorbed. So color band is appear when this wavelength or frequency is released, when electron is come from the excited state to the ground state. Okay, now, so I take an example of Lyman series here. Okay, in Lyman series what will happen? In Lyman series we consider the ground state is 1 N2, N3, N4, N5, N6, and N infinite are the excited state. When electron comes from 2 energy level 2 to energy level 1, energy level 3 to 1, energy level 4 to 1, energy level 5 to 1, energy level 6 to 1, or energy level infinity to 1. In all the cases, the frequency or wavelength observed are in ultraviolet region. In which region? That is in ultraviolet region. Similarly, in case of Balmer series, ground state is N2. Similarly, in Paschen series, the ground state is N3. Similarly, Bracht it is 4. For preferred it is 5. So Lyman series is lie in ultraviolet region, Balmer series is lie in visible region, Paschen, bracket, preferred, they all lie in IR. That is infrared region. Okay. Now we will proceed. This is a Rydberg formula. Okay. What is the use of this formula? This formula is used to calculate the wave number and wavelength of different series of line of the spectrum of hydrogen or hydrogen-like particles. Okay, we obtain hydrogen spectrum. We want to calculate the wavelength or wave number for each line. Then we will use Rydberg formula. What is the formula? Formula is nu bar. Nu bar is wave number is equal to 1 upon lambda is equal to r is equal r multiplied by 1 by n1 square minus 1 by n2 square. Here nu bar is wave number and this lambda is wavelength. Okay. Here you should remember one thing. N2 should be greater than that of the N1. This is the primary requirement. Okay. So the series obtained is as follow. For Lyman series, N1. N1 is ground state. Okay. And what is N2 is excited state. When ground state is 1, then excited state could be 2, 3, 4, 5 or infinity. In all the cases, the spectral region is ultraviolet. Okay. For Balmer series, value of N1 or ground state of Balmer series is 2 and excited state is 3, 4, 5, etc. And all the radiation comes in visible region, or we can say spectral region is visible. For Paschen, the ground state is 3, excited state is 4, 5, etc. up to infinity. Okay, here also infinity, here also infinity. So the spectral region is IR. For bracket, ground state is 4, excited state is 5, 6 and up to infinity. The spectral region is IR. For P fund, ground state is 5 and excited state is 6, 7 up to infinity. Again, the spectral region is IR. Okay, so here's the value of Rydberg constant. The Rydberg constant value is 1.097 into 10 to the power 5 centimeter inverse. This is the value in centimeter, or 1.097 into 10 to the power 7 meter inverse. This is centimeter inverse and this is in meter inverse. Okay, so here we will solve a question. Question is calculate the wave number for the longest wavelength transition in Balmer series of atomic hydrogen. So here we solve the question. For Balmer series, we already discussed that is value of N1 is 2. Okay. Rydberg constant value is 1.097 into 10 to the power 7 meter inverse. This is the formula we already discussed, that is nu bar is equal to 1 upon lambda r 1 upon n1 square minus 1 by n2 square. Here nu bar is a wave number. For the longest wavelength, the value of N2 is 3. Why it is 3? Because you know nu bar is inversely proportional to lambda. If it is low, then it is high. To make this wave number low, we take the value of N2 small. The smallest value for in case of Balmer is 3. So hence taking N2 is equal to 3, we get, this is the formula, we put the value. In this formula we will take wave number. R is a Rydberg constant 1 upon N1 square minus 1 by N2 square. So we will put the value. So this is the wave number. The value of Rydberg constant is 1.097 into 10 to the power 7 meter inverse 1 upon 2 square minus 1 upon 3 square. 2 is N1 and 3 is N2. So value comes to be 1.097 10 to the power 7 meter inverse 1 by 4 minus 1 by 9. So when we solve this equation, the value comes to be, that is nu bar 1.5236 into 10 to the power 6 meter inverse. So this is the wave number. Okay, this is our answer. I hope you like this video. Thank you. Thanks a lot. Class 11, Bohr's model of atom. In today's video, we will discuss Bohr's model of atom. In Neil Bohr developed a structural model for the hydrogen atom. The main postulates are: first, in an atom, the electron revolves around the nucleus in a certain definite circular path called orbits. So this is the nucleus around which these are the circular paths which are present. These circular paths are known as orbits. Okay. Second postulate is each orbit is associated with definite energy. These are known as energy levels or energy shell. These are numbered as 1, 2, 3, 4, etc. or K, L, M, N, etc. This is the nucleus, and this is the first energy shell, second, third, fourth, fifth, sixth. So these are the 6 energy shell. First energy level is also named as K, second is named as L, third is named as M, fourth is named as N. Okay. So only those energy orbits are permitted for the electron in which the angular momentum of electron is a whole number multiple of h upon 2 pi. Thus, the angular momentum of electron is mvr is equal to nh upon 2 pi. In this photograph, we are able to see this is the nucleus, and these are the first, second, third, fourth, fifth, sixth energy level. For energy level 1, we take n is equal to 1 value. Okay. In angular momentum formula, m is mass, v is velocity, r is radius of atom, n is number of energy level or shell, h is Planck's constant, and this is the value of pi. Okay, we substitute the value of n in this formula. We get m v r is equal to 1 h upon 2 pi, or m v r is equal to h upon 2 pi. So this is the angular momentum for first energy level. If we take n value 2, this is for energy level 2, the value comes to be m v r is equal to 2h upon 2 pi cross 2 to 2. Okay, so value become mvr is equal to h upon pi. So this is the angular momentum of second energy level. Okay, now we will move to the next postulate. As long as electron present in a particular orbit, it neither absorbs or loses energy. This is considered as a stationary state or ground state of that particular electron in that particular atom. Okay, so if any energy is absorbed from any external source, this electron is jumped from its ground state to excited state. So this is the excited state. This excited state is a temporary state. Okay, so after some interval of time, it loses energy and return back to its ground state. Okay, the energy release in the form of radiation. That radiation is electromagnetic radiation. So the concept of ground state and excited state is given by Neil Bohr. Okay, we can understand the concept of ground state and excited state by this animation, in which this electron is present at its ground state. When it gains energy from any external source, then it reaches to the excited state. You can see this image carefully. Okay, it absorbs energy and reaches to the excited state, and it is loses the energy and comes to the ground state again. Okay, whenever a electron loses energy from its excited state and reaches to its ground state, it releases energy in the form of radiation. This radiation is known as electromagnetic radiation. So in this photograph, you can see this is the excited state and this is the ground state. So electron jump from its excited state to the ground state and releases energy in the form of radiation. That radiation is known as electromagnetic radiation. Okay, now we will discuss the achievement of Bohr's model of atom. First is stability of an atom. Bohr gave the concept of ground state and excited state. Okay, on the basis of ground state and excited state, he is able to explain the stability of the atom. He says, when electron is present at its ground state, it never loses the energy or gain the energy. Okay, never loses or gain the energy. Okay, if it absorb energy from any external source, it jump from its ground state to excited state. Okay, so this is the excited state. This excited state is temporary state. After some interval of time, the electron will reaches to its ground state again, and it releases energy in the form of radiation. That radiation is known as electromagnetic radiation. So this is the explanation given by the Bohr's for the stability of atom. Okay, now he also calculated the energy of an electron in each energy level. Okay, so there E is energy in term of minus 21.8 into 10 to the minus 12 z square upon n square ergs per atom. Okay, here z is atomic number and n is number of orbit or number of energy level or shell. Okay, so if we convert this erg into joule per atom, the value will become minus 21.8 into 10 to the power minus 19. Okay. Here energy in terms of electron volt, the value is minus 13.6 into z square upon n square. Here z is atomic number and n is number of orbit or energy level. Okay. Similarly, if we want to calculate energy in term of kilojoule per mole, the formula is E is equal to minus 1312 n square z square. Okay, here z is atomic number and n is number of orbit or energy level. Okay, now calculation of Bohr's radius. So this is the formula. In this formula, this z is atomic number. This n is number of orbits or energy level. Here h is Planck's constant. This is pi. This is mass of electron. And this is charge on electron. When we calculate this whole part, the value comes to be 0.529 n square upon z angstrom. Here z is atomic number, n is number of orbit or energy level. Okay. So calculation of velocity of an electron. Velocity of the electron in different orbits will be calculated Vn 2.188 into 10 power 6 z upon n meter per square. Here n is number of orbit and z is atomic number. Okay, so these are the formula by which we can calculate the energy, radius and velocity of the electron. Okay, now limitation of Bohr's theory. The first limitation is the theory could not explain the atomic spectra of the atom containing more than one electron. As we discussed in this video, that Bohr is able to identify the structure of atom for hydrogen, that is only for one electron system. Okay, so he is not able to explain the atomic spectra of more than one electron. Okay, so not able to give the satisfactory explanation for Zeeman effect and Stark effect. What is Zeeman effect? When a spectral line is passed through the magnetic field, it's split into multiple lines. This is known as Zeeman effect. He is not able to explain this effect. Okay. Similarly, Stark effect. When a single line is passed through electric field, it's split into multiple lines. He is not able to explain the Stark effect. Okay. Third, it is not able to explain the shape of the molecule formed by the combination of the atom. So Bohr is not able to explain the shape of the molecule formed by the combination of atoms. Okay. The serious drawback comes from the new principles such as de Broglie's relationship and Heisenberg uncertainty principle. When these principles are discovered, there are so many drawbacks are observed in the Bohr's atomic model. These topics we will discuss in next video. Hope you are able to understand this topic. Thank you. Hello everyone. Class 11th Chemistry, Chapter 2, Structure of Atom. Our today's video is de Broglie's concept. According to de Broglie, just as light has dual nature, every material particle in motion has dual nature. It means, according to de Broglie, every material particle have wave nature as well as particle nature. De Broglie derived a relationship between wavelength and momentum of matter. This relationship is known as de Broglie relationship, which is given as lambda is equal to h upon mv, where h is Planck's constant, v is velocity, m is mass, and lambda is wavelength. Now we will derive the de Broglie relationship for photon. If we assume photon has wave character, the energy of photon is given by Planck's quantum theory, because this theory will explain the wave nature of light. Okay, so here E is equal to h nu. Here E is energy, h is Planck's constant, and nu is frequency. We consider it equation number 1. If photon is supposed to have particle character, the energy of photon is given by according to Einstein equation. Here E is equal to mc square. E is energy, m is mass, and c is velocity. We consider it equation number 2, where m is mass of photon and c is velocity of light. From equation 1 and 2, we get h nu is equal to mc square. We consider it equation number 3, but we know nu is equal to c upon lambda. We put the value in equation number 3, we get h c upon lambda is equal to mc square. We cancel c from c. If c, the velocity of light, is considered to be equal to the velocity of particle, then relationship become lambda is equal to h upon mv, that is mass and velocity product is considered as momentum. Thus lambda is equal to h upon p, or simply we can say lambda is inversely proportional to the momentum, where lambda is wavelength, m is mass of particle, v is velocity of particle, p is momentum of the particle. Now here we will discuss the significance of de Broglie's equation. It is applicable to all material objects, but it has significance only for microscopic particle. To understand it, we compare the wavelength of electron and a ball. Here, electron is a microscopic particle, whereas ball is a macroscopic particle. Here we take electron and a ball. Electron is a microscopic particle, ball is a macro particle or macroscopic particle. We know mass of electron, that is 9.1 into 10 to the power minus 31 kg. The mass of ball is 100 gram, that is 0.1 kg. We consider the velocity of electron is 10 to the power 5 meter per second. And we also consider the velocity of ball is 10 to the power 5 meter per second. It means the velocity of electron and ball both are same. The value of Planck's constant is 6.6 into 10 power minus 34 joule second. We know de Broglie's relationship, that is lambda is equal to h upon mv. We substitute the value of h, m and v in this equation, in this formula. Then we will find out 6.6 into 10 power minus 34 is the value of h. The value of m is 9.1 in 10 to the power minus 31 and velocity of light is 10 to the power 5. When we calculate it, the value comes to be 7.2 into 10 to the power minus 9 meter. Now we will calculate the wavelength for ball. The relationship we use is de Broglie relationship, that is lambda is equal to h upon mv. We substitute the value of h, m and v. Here h is 6.6 into 10 to the power minus 34, m is 0.1 and v is 10 to the power 5. The answer comes to be 6.6 into 10 to the power minus 38 meter. If we compare the wavelength of electron with the wavelength of the ball, we find out that the wavelength of electron is more significant as compared to the wavelength of ball. That is why we always says that is de Broglie's relationship is more significant, have more significant for microscopic particle as compared to the macroscopic particle. Now we will solve our numerical here. The question is, the mass of electron is 9.1 into 10 to the power minus 31 kg. If its kinetic energy is 3 into 10 to the power minus 25 joule, calculate its wavelength. Okay, we solve the question. Okay, so first from de Broglie equation we know the relationship that lambda is equal to h upon mv. Okay, so the given value in the question is the kinetic energy of the electron. The value is 3.0 into 10 to the power minus 25 joule. Since we know the relationship of kinetic energy, the formula of kinetic energy is half of mv square. Okay, so we have to calculate the velocity. The formula become whole root of twice of kinetic energy upon m. Okay, so when we take square both the side, then this velocity v will become v square, and due to square, this square whole root is cancel out. The value become v square is equal to twice of kinetic energy upon m. Okay, now we substitute the value of kinetic energy. The value of kinetic energy is 3 into 10 to the power minus 25, as well as mass of electron, that is 9.1 into 10 to the power minus 31. Okay, when we solve this equation, the value comes to be v square is equal to 65.9 into 10 to the power 4. Thus, on solving this, the value comes to be v is equal to 8.12 into 10 to the power 2 meter per second. Now, we will calculate the wavelength of the electron. Okay, so we know the relationship between the lambda and mv. Okay, so this relationship is de Broglie's relationship. Okay, here lambda is equal to h upon mv. Okay, so when we substitute the value of h, m and v that we calculated in previous slide, so the value become 6.62 is the value of Planck's constant in 10 to the power minus 34. Okay, so this is the value of Planck's constant, that is 6.62 into 10 to the power minus 34. Mass of electron is 9.1 into 10 to the power minus 31 and velocity is 8.12 into 10 to the power 2. Okay, when we solve this equation, the answer comes to be 0.0896 into 10 to the power minus 5 meter. So this is our answer. Okay, I hope you are able to understand this topic and like this video. Thank you. Thanks a lot. Hello everyone. Class 11th Chemistry. Our today's topic is Heisenberg's uncertainty principle. In this video, we will discuss Heisenberg's uncertainty principle. Heisenberg uncertainty principle. Heisenberg, a German physicist, in 1927 gave a principle about the uncertainty in simultaneous measurement of position and momentum of small particles. Heisenberg realized that in the world of very small particles, one cannot measure any property of a particle without interacting with it in a same way. This introduces an unavoidable uncertainty into the results. He gave a principle. That principle is known as Heisenberg uncertainty principle. It states that it is impossible to measure simultaneously the position and momentum of small particle with absolute accuracy. He gave a equation. The equation is the uncertainty principle equation. According to this equation, delta x dot delta p is equal to and greater than h upon 4 pi. Here, delta x is uncertainty in the position, delta p is uncertainty in the momentum, h is Planck's constant. He observed the product of uncertainty in the position and the uncertainty of the momentum is always constant and is equal to or greater than 4h upon 4 pi. It means delta x dot delta p is equal to constant, and this constant is h upon 4 pi. This constant is known as Heisenberg uncertainty constant. It is equal to h upon 4 pi. When we expand delta p, we can write this equation as delta x m delta v h upon 4 pi. Here delta x is uncertainty in position, whereas delta v is uncertainty in velocity. He also says that the more accurately you know the position, the less accurately you know the momentum. And vice versa. I already explained it to you. Delta x dot delta p is constant. It means if the value of delta x is low, then value of delta p is high, and vice versa. Okay, if value of delta x is low, then value of delta p is very high. We can observe it by this simple animation. Here you can easily observe when the value of momentum is less, the value of position is maximum. When value of position is minimum, the value of momentum is maximum. observe it. You can easily observe. Okay. So the uncertainty in position and uncertainty and momentum are inversely proportional to each other. Okay. What is the significance of Heisenberg uncertainty principle? Heisenberg uncertainty principle holds good for all objects, but it is significant only for microscopic particles. Now we will discuss a very important question. Why electron cannot exist in the nucleus? We answer this question. First, we consider let electron is present in the nucleus. Then, uncertainty in its position delta x is equal to 10 to the power minus 15 meter. Here, 10 to the power minus 15 is diameter of nucleus. Mass of electron m is equal to 9.1 into 10 to the power minus 31 kg. Now we calculate the uncertainty in velocity. According to uncertainty principle, delta x m delta v is equal to h upon 4 pi. Here delta v, that is uncertainty in velocity, will be equal h upon 4 pi m delta x. When we place the values of delta h, that is 6.6 into 10 to the power minus 34, 4, value of pi 3.14, mass of electron 9.1 into 10 to the power minus 31, and diameter of nucleus, that is 10 to the power minus 15, which is act as a uncertainty in position. When we calculate this equation, the answer comes to be 5.7 into 10 to the power 10 meter per second. The uncertainty in velocity is more than that of the speed of light, that is 3 into 10 to the power 8 meter per second. Thus, we can say that electron does not exist in the nucleus. Now we will solve one more question. The question is, a golf ball has a mass of 40 gram and a velocity of 45 meter per second. If the speed can be measured within an accuracy of 2%, calculate the uncertainty in its position. First, we will write the given values, that is mass of ball, that is 40 gram, or in kg its value is 0.040 kg. Velocity is given, velocity v 45 meter per second. Accuracy is given, that is 2%. First, we will calculate uncertainty in velocity. For that, we know uncertainty in velocity delta v will be equal to 45 into 2 divided by 100. Here 45 is velocity and 2 is accuracy. When we calculate it, the value comes to be 0.9 meter per second. According to uncertainty principle, we know delta x dot delta p is equal to h upon 4 pi, or delta x m delta v is equal to h upon 4 pi. Now we will calculate delta x, that is uncertainty in position, is equal to h upon 4 pi m delta v. We substitute the value of h, that is 6.6 into 10 to the power minus 34, for the value of pi 3.14, m 0.04 in kg, delta v, that is uncertainty in velocity, we already calculated, its value is 0.9. When we calculate this, the value comes to be 1.46 into 10 to the power minus 33 meter. So this is our answer. Okay, now we will solve one more question. A microscope using suitable photon is employed to locate an electron in an atom within a distance of 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? Okay, we answer this question. First, we will write given. For the given value is uncertainty in position, that is delta x 0.1 angstrom. When we change into meter, the value comes to be 0.1 into 10 to the power minus 10 or 10 to the power minus 11 meter. Planck's constant value is 6.6 into 10 to the power minus 34. The mass of electron m is 9.1 into 10 to the power minus 31 kg. According to uncertainty principle, delta x m delta v is equal to h upon 4 pi. We have to calculate uncertainty in velocity. Thus, equation become delta v is equal to h 4 pi m delta x. We place the value of h, that is 6.6 into 10 to the power minus 34, value of pi 3.14, value of m 9.1 into 10 to the power minus 31, and value of delta x, that is 10 to the power minus 11. When we solve it, the answer comes to be 5.79 into 10 to the power 6 meter per second. That is our answer. I hope you like this video. Thank you. Thanks a lot. Hello everyone. Class 11th, Chemistry, chapter 2, Structure of Atom. In today's video, we will discuss Schrodinger wave equation and quantum numbers. So we proceed to our topic. Our today's topic is Schrodinger wave equation. It was given by Erwin Schrodinger. Schrodinger wave equation is a mathematical expression describing the energy and position of the electron in space and time. It is based on the three considerations. They are as follow. First, there is a classical plane wave equation. Second, de Broglie's hypothesis of matter wave. And third is conservation of energy. This equation describes the motion of electron in three-dimensional space. It is written as del square psi del x square plus del square psi del y square plus del square psi del z square plus 8 pi square m s square e minus v psi is equal to 0. Here, del square is second derivative with respect to x. For this equation, it is with respect to x. In this, it is with respect to y. In this, it is with respect to z. Here, psi is a wave function, whereas z square is a position for this equation. For here, it is y, and this is for x. E is total energy of electron, and V is the potential energy. Okay. Now, significance of wave function psi. Wave function gives us the amplitude of wave. The value of psi has no physical significance. Significance of psi square. Psi square gives us the region in which the probability of finding an electron is maximum. It is also known as probability density. In short, Schrodinger wave equation is written as H psi is equal to E psi. Here H is Hamiltonian operator, that is a energy operator, whereas E is energy, that is a eigen value. Here psi is wave function. Okay, now we will move to our next topic, quantum numbers. It is a set of four numbers which give full information about any electron in an atom, or we can simply say quantum number will give us the complete address of an electron which is present in an atom. These are principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Now we will discuss first principal quantum number. Principal quantum number is denoted by small n. Its value are 1, 2, 3, etc. or k, l, m, etc. It will tell us about the shell to which an electron is belongs. Here the shells are k shell, l shell, m shell, and n shell. We give them the number 1, 2, 3, and 4. Okay, it determines the average distance of the electron from the nucleus. This is the distance of electron from the nucleus. So this is the radius of atom. This is the distance between the second energy level and the nucleus. This is the distance between the nucleus and third energy level, and this is the distance between the nucleus and the fourth energy level. It also determines the energy of the main shell in which electron is present. So the energy of fourth shell is more and energy of first shell is very low. Or we can simply say, as we move far away from the nucleus, the energy of the shell is increases. Or we can say the energy of fourth shell is more than that of the first shell. Okay, so the energy of first shell is low and energy of fourth shell is high. Okay, now the maximum number of electron present in the nth shell given by 2n square rule. Here name of the shell is given and maximum electron present in a shell is also mentioned. The shell given are K shell, L shell, M shell, and N shell. Here their number is K shell, N value is 1. For L shell, N value is 2. For M shell, N value is 3. For N shell, N value is equal to 4. 4. So we will calculate the number of electron in K shell. In K shell, the N value is equal to 1 according to the formula. 2n square is equal to 2 into 1 square, the value become 2. For L shell, n value is become 2 according to the formula 2n square. This 2 into 2 square is equal to 2 into 4 is equal to 8. Okay, so number of electron in K shell is 2, in N shell is 8. Okay, in M shell, N value is equal to 3 according to the formula 2n square, 2 into 3 square, that is 2 into 9, that is 18. So number of electron in M shell is 18. N shell, N value is equal to 4, 2n square, 2 into 4 square, that is 2 into 16, that is 32. So number of electron in N shell is 32. Okay. Now the azimuthal quantum number. Azimuthal quantum number is denoted by small l. In azimuthal quantum number, L is also known as orbital angular momentum or subsidiary quantum number. It determines the number of subshell present in any main shell. It determines the shape of the orbital, energy of orbital and multi-electron atoms along with principal quantum number. It also determines it. Okay. So there are shells, K shell, L shell, M shell and N shell. K shell is containing one subshell, whereas L shell is contain two subshell, that is 2s and 2p. M shell is containing three subshell, that is 3s, 3p and 3d, and N shell is contain four subshell, that is 4s, 4p, 4d and 4f. Okay. Now value of L is from 0 to n minus 1 for each value of n. Thus L is equal to n minus 1. The value of L for a particular orbital is generally designated by the letter S, P, D and F corresponding to L values. Here the value of L and subshell are given. If value of L is 0, then subshell is S. If value of L is 1, then subshell is P. If value of L is 2, then subshell is T. If value of L is 3, then subshell is F. If value of L is 4, then subshell is G. If value of L is 5, then subshell is H. G and H subshell are not used in the ground state of any known element. For the known atoms, only S, P, D and F exist. Okay. Thus, subshell present are in this chart principal quantum number n, L value and name of the subshell is given. Here the principal quantum number is 1, 2, 3 and 4. It means shell number 1, 2, 3 and 4 are involved. These are the L value which is already calculated. and these are the name of the subshell which is present in each main shell. Okay, we have to calculate the L value here. So before proceeding, we have to remember S, P, D and F. These notation are given to L value 0, 1, 2 and 3. Now we will calculate the L value with the formula L is equal to n minus 1. Here n value is equal to 1, L is equal to n minus 1, that is 1 minus 1 is equal to 0. Okay, so for first energy level or first shell, L value is 0. Here subshell is 1s, 1 for principal quantum number and s for 0 value of L. So name of subshell is 1s. Similarly, for second main shell, n value is equal to 2, formula L is equal to n minus 1, that is 2 minus 1 is equal to 1. It means it have value 0 and 1. Okay, 0 for S and 1 for P. So the here is the L value 0 and 1. Okay, so name of the subshell is 2s and 2p. Here 2 is principal quantum number and s and p is according to the these L value, s for 0 L value and p for 1 L value. Okay, now third main shell, n value is equal to 3, formula L is equal to n minus 1, that is 3 minus 1 is equal to 2. It means it have 0, 1 and 2 L value. So here is the answer. You can see 0, 1, 2 are the L value in main shell third. So these three are the principal quantum number, and S, P and D notation are given when L value is 0, when L value is 1 and when L value is 2. Okay, now n is equal to 4 for the fourth main shell. Okay, so we calculate by the formula L is equal to n minus 1. The value comes to be 4 minus 1 is equal to 3, that is 0, 1, 2, 3. For 0 we use S, for 1 we use P, for 2 we use D and for 3 we use F. So these are the 4 L value 0, 1, 2, 3, and these are the 4 are the quantum principal quantum number, and S, P, D and F are notation according to the L value. Okay, now we will move to the next slide. Azimuthal quantum number also determine the angular momentum of the electron in any orbital as formula capital L is equal to root of small l, L plus 1 h upon 2 pi. Okay, the number of orbital in a subshell can be calculated by the formula 2l plus 1. Okay, next is magnetic quantum number. It is denoted by small m or ml. It determines the number of orbital present in any subshell, the orientation of each orbital, and for a given value of L, the value of m is from minus L to plus L including 0. Okay, here the value of angular momentum quantum number or azimuthal quantum number is given. These are the number of orbital by the formula 2l plus 1, and these are the value of m, which is from minus L to plus L including 0. Here angular momentum quantum number value or azimuthal quantum number value are 0, 1, 2 and 3 for subshell S, P, D and F. The number of orbitals are here already calculated. So we will calculate it one by one by this formula 2L plus 1. If L value is 0, then 2 into 0 plus 1 is equal to 1. Okay. If L value is 1, then 2 into 1 plus 1 is equal to 2 plus 1 is equal to 3. If L value is 2, then 2 into 2 plus 1, that is 4 plus 1, its value is 5. If L value is 3, that is 2 into 3 plus 1, then 6 plus 1, that is 7. So S subshell is containing 1 orbital, P subshell is containing 3 orbital, D subshell is containing 5 orbital and F subshell is containing 7 orbital. The value of M is minus L2 plus L including 0. This is 0 for S. For P subshell where L value is 1, it is minus 1, 0 and plus 1. For D subshell where L value is 2, the value of M is minus 2, minus 1, 0, plus 1 and plus 2. And F subshell value where L value is equal to 3, the M will be equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3. Okay. Now spin quantum number. It is denoted by S or MS. It tell us about the spinning motion of the electron, that is electron move clockwise or anti-clockwise. Its value is either plus half or minus half. The arrow up is plus half and arrow down is minus half. Now we will solve some numerical problems. The question is, an electron is in one of the 3D orbitals. Give the possible value of N, L and M for this electron. The answer for the 3D orbital, 3D, here 3 is value of N and D subshell is involved. On the basis of that we can calculate the value of L. You know, S, P, D and F subshell are present in any main shell. The value of L in case of S is 0, for P 1, for D 2 and for F it is 3. Thus the principal quantum number value is 3 and azimuthal quantum number value is 2 because electron belongs to the D subshell. The magnetic quantum number value M is equal to minus 2, minus 1, 0, plus 1 and plus 2 because value of M is lie between minus L2 plus L including 0. Okay. Question number 2. Using SPD notation, describe the orbital with the following quantum number. These are the 4 different quantum number are given in 4 different part A, B, C, D. We will solve it. Okay. So we answer first, that is A part. A given value is N value is 1 and L value is 0. You know, if L value is 0, it belongs to the S and N value is 1. Before S we place 1. So the orbital is 1s. Okay. Similarly for B part, given value is N is equal to 3 and L is equal to 1. Okay. For L is equal to 1, it belongs to the subshell P and N value is 3. So the orbital is 3p. Okay. C, given value is n is equal to 4. The value of L is equal to 2. The orbital is 4d. How? D subshell is present when L value is equal to 2. So it is 4d. For D, N value is 4, L value is 3. So here F, if value is 3, L value is equal to 3, and this is 4. So the orbital is 4f. I hope you are able to understand today's topic. Thank you. Thanks a lot. Hello everyone. Class 11th, Chemistry, chapter 2, Structure of Atom. Our today's topic is atomic orbitals. First we discuss what is atomic orbitals. Region of space around the nucleus of an atom where probability of finding an electron is maximum is known as atomic orbital. Here are atomic orbital is given. This is the nucleus around which the probability of finding an electron is maximum. Okay, this is three-dimensional area of space. This white part is act as a nucleus, and this red part is the electron density. Okay, so here probability of finding an electron is maximum. So this is the white part is nucleus, and around it is a electron density or probability density, where probability of finding an electron is maximum. You can see here there is a white region. This white region is known as node. So it is node, area of space around the nucleus where probability of finding an electron is 0, or we can simply say orbitals are found to have a region or space within it where probability of finding an electron is 0. This is called nodes. Okay, so at node the probability of finding of electron is 0. Okay, here radial nodes. Radial nodes occur when the probability of the electron is 0 on a spherical surface on a particular radius. The number of radial nodes are n minus L minus 1, whereas angular nodes occur when the probability of the electron is 0 along the direction specified by a particular angle. They can be calculated as the number of angular nodes is equal to L. Here L is azimuthal quantum number. So total number of nodes is equal to n minus 1. Okay. Now degenerate orbitals. The orbital having the same energy are called degenerate orbitals. For example, p subshell has 3 degenerate orbital, d subshell has 5 degenerate orbital. Here is the example. P subshell has 3 degenerate orbital, whereas d subshell have 5 degenerate orbital. Similarly, F subshell is have 7 degenerate orbital. It means in p subshell all the 3 orbital have the similar energy. In d subshell all the 5 d orbital have the similar energy. In F subshell all the 7 orbitals have the similar energy. Okay, now Pauli exclusion principle. According to the Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum numbers, or an orbital can have maximum 2 electrons, but these must have opposite spin. How we will understand? We'll understand like this. An orbital can occupy maximum 2 electrons, and these 2 electrons must have opposite spin. In first case, in 1s, the 2 electrons have opposite spin, but at 2s there are electrons having the similar spin. That is why this is not allowed. Whereas in second case you can see the electrons are having opposite spin in case of 1s as well as in 2s. Okay, now there are three subshell: p subshell, d subshell, f subshell, which having following orbitals. So the filling of electron is like that. The an orbital can occupy maximum 2 electron that must have opposite spin. Okay, like this, like this. Okay, so you can see in p subshell there are 3 orbital, and I fill 2 electron in a single orbital, and they must have opposite spin. Similarly for the d, this upward arrow and downward arrow will indicate that they have different spin. Okay, like this. Okay, similarly for f, they have opposite spin. So the Pauli exclusion principle, an orbital can have maximum 2 electron, and these must have opposite spin. Okay, now shapes of atomic orbital. So here we will discuss first s orbital. All s orbitals are spherical in shape. Okay, however, they are differ in energy and number of nodes. Okay, 1s has no node, 2s has one node, 3s has two node, and so on. Okay, so these are the energy. The energy of 3s is more than that of the 2s, and energy of 2s is more than that of the 1s. Now we will move to the next. In this slide, we will calculate the number of nodes. We know the formula of calculation of node is node is equal to n minus L minus 1 for radial node. So these are the radial node around along the spherical area. So for 1s, value of n is 1 and value of L is 0. So we place the value 1 minus 0 minus 1 0. So in case of 1s, the number of node is 0. In case of 2s, we write the formula node is equal to n minus L minus 1 for 2s. The value of n is 2. The value of L is equal to 0 because it belongs to the S subshell. Okay, so 2 minus 0 minus 1. So number of node is 1. Okay, now for 3s, that is node is equal to n minus L minus 1. Here the value of n, that is quantum principal quantum number, is 3. The value of L is 0, that is azimuthal quantum number value is 0. 3 minus 0 minus 1, net value is 2. So number of node in 3s is 2. So you can see in 3s there are 2 nodes, whereas in 2s there is only 1 node. Okay, now for p orbital, all the p orbital are dumbbell in shape. The 3p orbital differ in their orientation. You know, p subshell contain 3p orbital and they are differ in their orientation. They lie along the axis, are called px, py and pz. Okay, 2p has no node, 3p has one node, 4p has two node, and so on. Okay, so this is the p orbital which having the dumbbell shape. You can see in this animation, this is a dumbbell shape, this is the 3D. Okay, so these are the 3p orbital, that is px, py and pz. In case of px, the dumbbell are along the x-axis. In py, the dumbbell are along the y-axis. In pz, dumbbells are along the z-axis. Okay. Now d orbitals. There are 5 d orbitals, that is dxy, dyz, dzx, dx square minus y square, and dz square. D orbitals have clover leaf shape with 4 lobes, like this. This is the 3D diagram for d orbital, in which clover leaf like structure you can observe. Okay. dxy, dyz, dxz have lobes between the axes, like this. This is the clover leaf like structure. Okay. Whereas dx square minus y square has lobe along the axis. In dz square has 2 lobe along z-axis and a donut shaped electron cloud in the center, like this. So these are the z-axis in which 2 lobes are present, and this is a donut shape. So this is the image for d orbital. So this is dx square minus y square, where x and y axis having the orbital lobes. Okay. In dz square, orbital lobes are along the z-axis, and this is a donut shape. In dx square and x and y, dx and y, they are in between the x-axis and y-axis. In dxz, the lobes are present between z and x-axis, whereas dyz, the lobes are between z-axis and y-axis. Okay. So thank you. I hope you able to understand this video. Thank you. Thanks a lot. Hello everyone. Class 11th, Chemistry, Chapter 2, Structure of Atom. Our today's topic is rules for filling of electron in orbitals. For filling of electron in an orbital, we follow the following rules. They are Aufbau principle, Pauli exclusion principle, and Hund's rule of maximum multiplicity. First, Aufbau principle. According to Aufbau principle, the orbitals are filled in order of their increasing energy. It means the lower energy orbital will fill first and higher energy orbital will fill later. Here we will follow n plus L rule, where n is principal quantum number and L is azimuthal quantum number. It states that lower the n plus L value, lower is the energy, or if n plus L value is higher, then energy of the orbital is higher. Here we take an example of 1s and 2s. In case of 1s, 1 is the principal quantum number whose value is n. On the basis of s, we can understand the value of L is 0. So n plus L value in case of 1s is 1 plus 0 is equal to 1. Similarly, in case of 2s, 2 will tell us the principal quantum number value, that is n, and on the basis of S we can find the value of azimuthal quantum number L value, that is 0. So by putting the formula n plus L, that is 2 plus 0, the value comes to be 2. So here we can observe the n plus L value for 1s is 1 and for 2s is 2. So energy of 2s is higher than that of the energy of 1s orbital. Okay, here if two orbital have same n plus L value, the orbital with lower value of n has lower energy. For example, 3s and 2p. In case of 3s, 3 will tell us the value of quantum number, that is principal quantum number, n, and on the basis of s we find the value of azimuthal quantum number L is 0. According to the formula n plus L, 3 plus 0, value comes to be 3. In case of 2p, the n value is 2 and according to p, L value is 1. So according to the formula n plus L, 2 plus 1, that is 3. So value of 3s is 3 and value of 2p is 3. Due to the lower n value, the energy of 2p is less than that of the 3s. Okay. Thus, the order is the energy of 1s orbital is least and energy of 5d orbital is maximum. Okay. So here, as we move downward, the n plus L value is keep on increasing. Thus, we can say that the 1s have the lower n plus L value or having lower energy orbital. The filling of orbital takes place like this. First 1s is filled, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and 8s. So we can say that 1s is having the lower energy value, or it is a lower energy orbital, whereas 8s is higher energy orbital. Observe how they are filling. First 1s, then 2s, and so on. Observe it carefully. Now we will discuss Pauli exclusion principle. According to the Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum numbers, or an orbital can have maximum 2 electrons and these must have opposite spin. Okay, here we can see in case of 1s we observe there are 2 electrons, they have opposite spin, but in case of 2s there are 2 electrons which having the same spin. It means it will not follow the Pauli exclusion principle, so this is not allowed during the filling of electron in orbital. But in second case we observe in case of 1s both the electron have opposite spin. In case of 2s both the electron have opposite spin. So this method is allow for filling of the electron in the atomic orbital. Here we will take few example for p subshell, d subshell, and f subshell. P subshell is having the 3 orbital in which they can each orbital can occupy maximum 2 electron that must have opposite spin. The upward arrow and downward arrow is suggest us they have opposite spin. Similarly, in case of D, it have 5 atomic orbital. D subshell is having the 5 atomic orbital, and each orbital can have maximum 2 electron that must have opposite spin. If spin is not opposite, then the filling of electron is not allowed. Similarly, in case of F, which having the 7 atomic orbital, so each atomic orbital is having uh, can have maximum 2 electron that must have opposite spin, like this. Okay, now we will discuss Hund's rule of maximum multiplicity. Pairing of electron does not occur in orbital such as p, d and f of the same subshell until each of them is first singly occupied. Or we can simply say pairing will not take place until unless each degenerate orbital must occupy a single electron. Here p subshell, d subshell and f subshell is given. P subshell is having the 3 orbital. These 3 orbitals having similar energy, that is why we call degenerate orbital. So pairing will not take place until each orbital is singly occupied. Now they are singly occupied. Now pairing will takes place. Okay. Now pairing will takes place. So here we follow 2 rules. Hund's rule as well as Hund's rule as well as Pauli exclusion principle. Okay. So according to Hund's rule, each orbital must have a single electron or singly occupy. After that, pairing will takes place. According to the Pauli exclusion principle, each orbital can have maximum 2 electron that must have opposite spin. Similarly, in case of F, first we will add 1 electron in each orbital, and after that pairing will takes place. Okay. Okay. Now, next here. So if we do pairing like this, it is a correct method in which electron occupy first singly, then pairing will takes place. If we pair up like this, it is not allowed because it is not follow Hund's rule. This orbital is vacant. Before pairing, each orbital must occupy 1 electron. So it must occupy 1 electron before pairing. Okay. So here we can understand by small animation. Okay. So here is filling of electron in orbitals. See here, 1, then pairing, 1, then pairing, 1, 1, 1. Hund's rule. Pairing, pairing, pairing. So this is Pauli exclusion. Singly occupy, pairing, single, single, single. Now pairing, pairing, and then pairing, then singly occupy, and then pairing. So this is the method how we will fill the electrons in atomic orbitals. Okay. So observe it carefully. Hope you will understand it very well. Are you able to understand it? Observe it carefully. See, they are following Hund's rule as well as Auber principle as well as Pauli exclusion principle. They fill lower atomic orbital first, and after that they follow another rule, that is Hund's rule and Pauli exclusion principle. Now we will discuss electronic configuration of element. The distribution of electron of an atom into different shells, subshells and orbitals is called electronic configuration. The complete electronic configuration is obtained by following the rules for filling of electron in orbitals. Here NLX is the form by which we represent the electronic configuration of elements. Here N is energy level, or we can say it is a principal quantum number, whereas X is number of electron in this orbital, whereas L will tell us type of orbital by giving the information about the subshell and type of orbital. It is azimuthal quantum number. Here we take an example of hydrogen. So this is the electronic configuration of hydrogen. So first atomic orbital is 1s. The atomic number of hydrogen is 1. That is why it occupies only one electron. Here 1 will tell us the energy level, that is its principal quantum number. Here S will tell us the type of orbital or subshell, that is S, and 1 indicate the number of electron in this orbital or in subshell. Okay. Now here the filling of atomic orbital takes place like this. First 1s will fill, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s, then 4d, 5p, 6s, 4f, 5d, 6p, 7s, then 5f, 6d, 7p, and then 8s. So here we will write the electronic configuration of few elements. For example, hydrogen with atomic number 1. So 1s will carry maximum 2 electron, out of which when 1 electron is present, the electronic configuration is 1s1. Similarly, in case of helium, it have atomic number 2. So we represent here 2. S can occupy maximum 2 electron. Okay, so electronic configuration is 1s2. In case of lithium, atomic number is 3. This S can occupy maximum 2 electron. That is why third electron will reaches to the next shell, that is 2s. So electronic configuration is 1s2, 2s1. Similarly, in case of beryllium, atomic number is 4. S can occupy maximum 2 electrons. So first we fill 1s2 and then 2s2. After that there is a carbon, atomic number 6. So 1s can occupy maximum 2 electron, 2s can occupy maximum 2 electron, and p can occupy maximum 6 electron. So these 2 electron, 2 plus 2, 4. Remaining electron are 2. They are present at 2p. Okay. Now we take another example, chlorine, which having 17 electron. We know 1s can occupy maximum of 2 electron, 2s can occupy maximum 2 electron. So 2 plus 2. How many electron can p occupy? 6 plus 6. How many 3s can occupy? That is 2. How many p can occupy? 6. So there are 2, 4, and 1, 5. So we will make the sum total 2, 2, 6, 10, 12, and 5, 17. So we fill the electron according to the capacity of each orbital. So S can occupy maximum 2, that is why we can provide maximum 2 electron. P can occupy maximum 6 electron, that is why we give 6 electron to P. After that, electron will fill to the higher energy orbitals. Okay. So in next
slide we will discuss the numerical. Here is the numerical. The question is, write the electronic configuration of the following ions. The ions given are H minus, Na plus, O2 minus, F minus. So first we do the first part, A, H minus ion. As we know, the electronic configuration of hydrogen is 1s1. Okay. A negative charge on the species indicate gain of electron. So 1s1 plus 1 is known as 1s2. So its electronic configuration is 1s2. So in case of H minus, electronic configuration is 1s2. Okay, now Na plus, the electronic configuration of sodium is atomic number 11, that is 1s2, 2s2, 2p6, 3s1. This is the electronic configuration in case of sodium. A positive charge on the species indicate the loss of an electron by it. So we minus one electron. So minus minus is cancel out. Thus the electronic configuration of Na plus is 1s2, 2s2, 2p6 and 3s0, because we eject electron from this 3s outer shell, or we can simply write 1s2, 2s2, 2p6. Okay. Now in case of O2 minus ion, the electronic configuration of O2 atom is, the atomic number of oxygen is 8. So 1s2, 2s2, 2p4. Here di-negative charge on the species indicates that 2 electrons are gained by it. So 4 plus 2, that is 6. So value will become, in case of O2 minus, electronic configuration will become 1s2, 2s2, 2p6. So 4 plus 2 is 6. Okay. Now F minus ion. The electronic configuration of F atom is, F is having atomic number 9. So electronic configuration is 1s2, 2s2, 2p5. Okay. A negative charge on the species indicate the gain of electron by it. So 5 plus 1 is equal to 6. So there are 6 electrons in the P. So here's the answer. Electronic configuration of F minus ion is 1s2, 2s2, 2p6. So by this numerical we are able to understand it. If cation is present, we have to minus the number of electron as positive charge is present on the cation. If anion is present, we have to add equal number of electron as the charge present on the anion. I hope you understand this video. Thank you. Thanks a lot.
Hello everyone. Welcome to our YouTube channel. My View My Channel, in association of Teaching Point. Like, subscribe, comment. Visit our website www.teachingpoint.org.in.
Class 11th, Chemistry. Today's topic is black body radiation and photoelectric effect.